Okay, so we have started our discussion of periodic functions, and our goal is to be able to expand, periodic functions in a Fourier series, right? So before we give out the prescription for doing this, it's useful to look at functions and continuity a bit, look at it closely, and also bring in a linear vector space perspective, for these functions, right? Which is the objective of this lecture. Okay, so in physics we typically work with nice well-behaved functions, and in particular we don't worry too much about artificially constructed functions which have very strange properties, right? Although these are important when you're building a general theory, and mathematicians often worry about whenever you have a broad statement or a broad structure that you build, so they come up with examples which can break apart the structure, so that they worry a lot about how things can be stated very precisely, right? And so a lot of work goes into making things extremely tight, right? Which is not the approach that we will take, right? We are interested in the details and in being correct, but by and large, from a physicist's perspective, we like to work with smooth functions, right? The word smooth itself will indicate more carefully what it means, right? So let's define a few terms. So let's think of a function which is defined on some open interval and containing a certain point x0. We say that this function is continuous, right? Intuitively we know what continuity is. So the key point is that the value of this function, not only at x0 is known, but the limit of this function slightly to the right of the point of interest is also well defined. And not only is it well defined, its value slightly to the right of where you are is the same as the value of this function slightly to the left, right? That's the notion of continuity, right? So a function which is not continuous at a point is said to be discontinuous at such a point, right? So not all discontinuous functions are discontinuous in a violent way. There is a relatively benign kind of discontinuity which we would like to allow, because these are also the kind functions which appear all the time in physics, right? So these are functions which which have what are called simple discontinuities, right? So you say that a function has a simple discontinuity at a point x0 if the limit f of x0 plus exists and the limit f of x0 minus exists, right? So if it were a violent kind, then one or both of these limits would not exist, and then it would require a different kind of treatment, such functions with such more violent kinds of discontinuity, right? Among functions with simple discontinuities, right, there again there's a further classification, right? A simple discontinuity itself is of two kinds, right? One of them is what is called a removable discontinuity, right? So everything is good with this function except that you have defined the value, you have given the wrong value for this function at just one point, right? Everything else otherwise is just nice and continuous about this function. So only problem is that the limit f of x0 plus it exists, limit of f x0 minus also exists, and they're equal, but only the value of this function is some other value than these two, right? So it's called a removable discontinuity because it's removable, right? You could just redefine this function by shifting the value to the value of these two limits, and then the discontinuity is gone, right? Such a discontinuity is called a removable discontinuity, right? And then there is another kind which is also a simple discontinuity, which is called a jump discontinuity, right? So f of x0 plus and f of x0 minus, they exist, but they are not the same, and it doesn't matter what value you ascribe to f of x0. There is no simple way to fix this discontinuity. It is a discontinuity, but it's something that you can work with, right? F of x0 plus exists and f of x0 minus also exists. They are not equal, and f of x0 you can choose to be some value, right, that lies in between. Oftentimes one chooses it to be, the average of f of x naught plus and f of x naught minus, right? We will come across this later. So the key point is that, if a discontinuity is simple, then, we can work with this, right? These kinds of discontinuities appear all the time, and we want to include this in our discussion, right? So that is why we are making these definitions right away. And so let's look at a few examples. So if you have a function like f of x equal to x squared, it's clearly a continuous function for all real values of x, no problems. But if you say f of x is x squared, if x is not equal to 1, but at x equal to 1, you say that this function is minus 1, right? So clearly there's only a problem at x equal to 1, because according to this function it should be 1, so this is what would be a removable discontinuity, right? It can be removed if you simply redefine this function to be 1 at x equal to 1, and then you don't need to make this distinction between x not equal to 1 and x equal to 1. It's something that you've healed. On the other hand, if you have a function which is plus 1 if x is greater than or equal to 1, and if it is minus 1 if x is less than 1, this is a jump discontinuity, right? So this is like a step function. And so here we have defined the value of this function to be equal to the right limit at x equal to 1, right? So but it doesn't matter, it's a jump discontinuity, right? So I have also given you one example of a more violent kind of a discontinuity, 1 over x. It has a discontinuity at x equal to 0, but it's not simple because the limit does not exist in its vicinity, right? So if it's a simple discontinuity, we will be able to work with these functions even in the context of Fourier series, right? So that's coming ahead. So let's look at a few more definitions. So a function is said to be piecewise continuous on an interval a comma b if f is continuous in this entire interval except at a finite number of points, right? It has a bunch of discontinuities, but the number of discontinuities is finite. You cannot have arbitrarily large number of discontinuities. There's a finite number of them, and each of these discontinuities is simple, right? Then you have a piecewise continuous function. These are also functions which we can work with. Okay, let's look at a few examples. So if f of x, so it's the same examples, we look at them again now that we have this notion of piecewise continuous. So if you have f of x equal to x squared, x not equal to 1 and is minus 1 if x equal to 1, it's piecewise continuous, right? The only difficulty is at x equal to 1. So it's piecewise continuous in this interval 0, 2. On the other hand, if you have minus 1 and x squared, the second example, it's piecewise continuous again. There's a jump discontinuity, but it's piecewise continuous, right? So if there is a finite number of discontinuities, it's not a problem. And here there is just one discontinuity, and that's a jump discontinuity. But on the other hand, f of x equal to 1 over x is not going to be piecewise continuous, provided you have looking at an interval which includes the origin, right? Because there is there is mess which is there at the origin, and that's not an easy kind of mess to deal with, right? So these are the type of discontinuities which which we would like to avoid, right? In you can come up with complicated functions, something like sine of 1 over x, right? You can think of functions of this kind, right? So you can come up with weird functions like if f of x is a certain value, if x is rational, and if x is irrational, it's another value, and so on, right? So these are the kind of constructions which would be of more of interest for a mathematician. So we will keep such functions aside and look at these smooth functions, right? When I talk of smooth, let me define the word smooth also a little more carefully here. So not only a function which is piecewise smooth continuous is interesting, but in fact there are functions which are piecewise smooth are even more interesting, right? These functions not only are piecewise continuous, but they are also their derivatives are also piecewise continuous, right? So these are called piecewise smooth functions on some interval a comma b. Function is piecewise smooth if it is piecewise continuous and its derivative is also piecewise continuous, right? So it turns out that the set of all piecewise continuous functions on a comma b, along with scalars drawn from the real field, they form a vector space, right? So it's something that we can verify, right? What do we have to verify? If you take any two such vectors from this, this box of vectors and add them, you should be able to get another vector which also lies in the same box, right? So which is true, right? Closure under vector addition is true because sum of any two piecewise continuous functions is also going to be piecewise continuous. If you take any piecewise continuous function and multiply by a real number, you'll get another function which is also piecewise continuous. So closure under scalar multiplication to holds, and indeed there is a null vector which is just the function f of x equal to 0. There is an inverse vector also. You can check for any function and such that if you add the inverse to this vector, you'll get back the 0 vector. So an important observation to make is that this is an infinite dimensional vector space, right? So some thought also reveals that in fact the set of piecewise smooth functions is a subset of this, and in fact it's a subspace, because again you can verify closure under vector addition. If you take two piecewise smooth functions and add them, you'll get another piecewise smooth function, right? Closure under vector addition and scalar multiplication, and so it forms a vector space. So it forms a vector space, and in fact we can also define an inner product for this vector space, right? So if we think of a vector f1 for the function f1 of x, and f2 is another piecewise continuous function, then we can define the inner product as, inner product of f1 f2 is this integral a to b f1 of x times f2 of x dx, right? Right now I'm just thinking of all these are real valued functions and all the scalars are real, right? It's possible to also come up with a somewhat more to extend this definition when you're working with complex scalars, and then you'll have to introduce a complex conjugation and all. So but for now let's just say that we are working with the real field, and so we have this inner product is defined like this, and you can verify that this is a valid inner product, right? So why do we bother about thinking about this as a vector space, and thinking of all these the notion of an inner product and so on, right? So we will see ahead that it's useful to bring in our linear algebra understanding, and when we develop this prescription for your series, we will also use our insights from linear algebra so that we have a deeper understanding of what is going on, right? So there are two aspects to this. One is the operational aspect. Given a function, we would like to be able to work out the Fourier series, but also it's since we already have all this nice training in linear algebra, it's useful to see that there is this underlying algebraic structure to all of this, right? So that's the spirit in which we have introduced this lecture. In the next lecture, we will look at the prescription for working out the Fourier series of a periodic function. That's all for this lecture. Thank you.